Hello everyone. Today I will be talking on our recent work, detection and elimination of systematic labeling bias in code review recommendation systems. Let me quickly recap what is code review and who is a code reviewer. Code review is a process to reduce bugs in software systems, and code reviewer is responsible for performing such code reviews and also responsible for the quality of the code which is being reviewed. And here's an example of typical code review scenario. Author creates a pull request, and then team leader, it doesn't necessarily need to be a team leader, it can also be someone else in the team, assigns a reviewer, and this reviewer gives some feedback to the author, and according to this feedback, author makes some changes and sends it back to the reviewer. This cycle continues until the reviewer is being satisfied with the quality of the code. In literature, there are several code review recommendation techniques exist. We divide them into two categories, optimization-based and learning-based. Optimization-based are more heuristic-based techniques and learning-based are more machine learning-based techniques. And these techniques are helpful for software teams to assign qualified code reviewers. Ground truth can be defined as objectively correct labels. It means that it doesn't depend on any subjective opinion. Ground truth in software engineering is, however, a bit different than that, as there is more room for human aspects, which leads to subjective opinions and which might cause ground truth problems. Labeling bias is kind of labeling error, and systematic labeling bias is when labeling systematically deviates from the objective from the ground truth, and therefore systematic labeling bias makes ground truth unreliable. Here's an example from code review from Qt Creator bug datasets. Here author makes comment, I would like to push this and do actual cleanup in master, which is a bad practice. However, here code reviewer gives +2, meaning that it confirms the pull request. And another example is author refers to the code reviewer with his name and says, please confirm this pull request, and then the reviewer confirms this pull request. These two R's are labeling biases, as the code review is not properly being done, therefore the code reviewer is not the qualified one. And here another example, qualified reviewer gives an appropriate comment to the pull request, and here non-qualified reviewer gives LGTM or no comment to the pull request, and these two pull requests are associated with reopened issue. However, on the other hand, this this pull request is associated with non-reopened issue, which I will talk into later. These CRR techniques, they evaluate their models based on the datasets from either open source or industry, and these techniques assume that datasets represent the ground truth. However, as we saw in previous examples, such datasets might include systematic labeling biases, and that situation leads to poor performance in real life. Therefore, our research questions are, how can we eliminate the systematic labeling bias in code review recommendation datasets? And the second question is, how does systematic labeling bias elimination affect the performance of code review recommendation techniques? We define purpose of code review as successful pull request, and pull request is successful when the associated issue is not reopened. If PR is not successful, then the label, in that case assigned reviewer, is not qualified. And not qualified reviewer assignments leads to labeling bias, and in general systematic labeling bias. To remove this bias, there are several methods that can be applied, and first one is manual correction, correcting labels manually, and the second one is removing such labels. And here's an example of manual correction. An additional expert can check when PR is closed, and the second one is we can assign multiple independent reviewers to a PR, and then we can pick out of the best one. And the third one is one expert can manually correct and clean reviewer assignments. But here the problem is about scalability. One expert cannot correct and clean reviewer assignments manually with 10,000 pull requests. Therefore, our debiasing approach is based on the removal of unsuccessful PRs. Again, unsuccessful PRs is when the associated issue status is from close to open. Here's a visualization of it. Here is the issue status diagram, and when the status goes from close to open, the issue is being reopened. And here's another example of non-qualified reviewer assignment. When a bug is introduced, author writes some code and it sends it to the reviewer, and then at the end of some cycles, reviewer approves it. It is being merged to the mainline, and then after some time, the same bug is reopened. There might be several reasons why this bug is reopened, and one of them is that the reviewer assignment is not qualified assignment, labeling bias. And here is a visualization of our approach. These circles, they represent PRs with non-reopened associated with non-reopened issue, and then these crosses represent pull request with associated reopened issue. And before debiasing, PR datasets include all PRs with associated reopened and also non-reopened. After we apply our debiasing in the datasets, we only have PRs associated with non-reopened issue. We evaluate our approach on two datasets, two open source datasets, Qt Creator and Hive. And we evaluate our approach with 5 different coding recommendation techniques: profile-based, arrest trace, naive bias, K9, decision tree. These 2 R's are optimization-based ones, and these 3 ones are learning-based ones. And our performance measures are top K, top 1, top 3, top 5, and MRR, mean reciprocal rank. And I also should mention that in our 2 datasets, we have observed low unsuccessful pull request rate, 5% to 7%. However, in literature, unsuccessful PRs are significantly more, between 15% to 25%. Therefore, we have undersampled our data by randomly removing successful pull requests. And here you can see our results before debiasing and after debiasing, and you can see the constant improvements here. For example, for naive bias one, it was 23 before debiasing, and after debiasing it's 27, and for 5NN it was 34, and it is changed to 38 after debiasing, and it goes like this. And also one observation can be done here is that these 3 ones are learning based ones, and we see large improvement more than the optimization based ones, here in our case profile based and arrest trace. And then we ask ourselves, does debiasing actually work, or was just coincidence? And to analyze this, we divided our datasets into several subsets. This is our original datasets, and then we do balancing to simulate real-world environment. And then here, reduced unbiased, when we randomly remove unsuccessful pull requests and also successful pull requests. And balanced debias is when we only remove unsuccessful pull requests. And reduced bias is when we only remove successful pull requests. And the number of removal here is equivalent to the number of unsuccessful pull requests. And here you can see in the results that the worst performing one is reduced biased, in our case when we only remove the successful pull requests. And the second worst one is here reduced unbiased, and reduced unbiased is when we randomly remove successful and unsuccessful ones. And the third one is balanced one, here after we apply balancing, And the most best performing one is balanced debiased when we only remove unsuccessful pull requests from the data sets. And all, to analyze how code reviewers are effective on pull requests, we did two analyses. And the first one is 45 of the bugs are reopened on the same day, and 80% of the bugs are reopened within 24 days. 45% is here important because it means that there's a problem that the code reviewer probably misses something, and then when it goes to production, something exploded and it is reopened on the same day. And here in the second analysis, quality analysis, we manually check the reopened code reviews, code reviews of reopened issues, and then we analyzed 40 data points. It is equivalent to 10% sample of Qt Creator. And then we have observed that 32 data points has in fact poor reviews according to the criteria we used. We divided the category into three: superficial, overruled, and poor effort. And here, code review to conclude, we can say that code review recommendation techniques build and evaluate their models on unreliable ground truth data, which is systematic labeling bias. And to remove such bias and to detect also such bias, we have introduced an approach which is based on debiasing method, which is based on the removal of unsuccessful pull requests. And again, overall, we have analyzed our method in two open source projects, Hive and Qt Creator, on 5 different code recommendation techniques: profile-based, RS-trace, naive-based, KNN, and decision tree. And we have observed up to 26 improvements. And these improvements are marginal on optimization-based CRR techniques, in our case profile-based and RS-trace. And it was large on learning-based CRRs, which is naive bias, KNN, and then decision tree. And as a future work, we are planning to add more data sets, especially we would like to use some commercial systems which might represent more industrial environments, more than open source data sets. And the second one is we would like to provide tool support for automated debiasing. And then the third one is we are interested in if there is any ground truth applications in other domains. And if you scan this QR code, you can reach out our preprint version. And thank you.